Okay, so if I had a coordinate plane here, you don't need to draw this. I'm just kind of reviewing what we talked about yesterday. All right. So if I took a linear equation, so something, I think the one that we used was x over 12. Okay, that's the exact same thing as y equals 1/12 x. 1/12 is the slope. Okay, so this, if we were graphing this line, it has a y-intercept of 0, and its slope is 1 up and 12 to the right. So something like this. It's a real shallow line. Okay. Now, if we took that line that's linear and we graphed its reciprocal. So if I took the reciprocal of this, all that means is I'm just reversing x and y. I'm swapping them. So the 12 is here and the x is down here now. Now, if I solve this equation, if I multiply both sides by x, I get x times y equals 12. So what that tells me is the numbers that are on this graph are numbers that when you multiply them, you get 12. So like 1 and 12, 2 and 6, 3 and 4, 4 and 3, 6 and 2, 12 and 1, and then also the negatives. Okay. Now when we took those and we put them into Desmos and we graphed them, we got a shape that looked like this. And if I kept doing this list and I did the negatives that multiply together to be 12, -1, -12, -2, -6, etc., then that created another branch of the graph right here. So a line, when you took the reciprocal of a linear function, it turned into a hyperbolic or a hyperbola. That shape right there is a hyperbola. And remember, we got a hyperbola when you took two cones. When you took a cone, remember a cone is actually looks like that. And if I cut that cone this way and looked at the cross sections, I'd have a parabola there. It looks like a parabola there and a parabola there. And when you look at it, it looks like this. That's called a hyperbola. So the hyperbola, the reciprocal function, this right here, is a hyperbola. Okay, this was the linear. That was a line. And when we did this, it turned into a hyperbola. So it's like, how could something that's straight turn into two things that are curved? Mystery. Okay, well, today we're going to look at why that actually happens. Okay, but that's sort of where we were yesterday. And we found out that if I took y equals and I made it a negative, then all it did was take that graph and flip it over the x-axis. So it ended up looking something like this purple graph here. Okay, that was y equals -12x. And the red one was y equals +12x. So if it's positive, it lives in quadrants 1 and 3. And if it's negative, it lives in quadrants 2 and 4. Okay, all righty. So that's kind of yesterday in a nutshell. Okay, so today what we're going to do is first start with taking a reciprocal function and identifying its domain and its range. All right. So we want to go. Got this opened. So we're actually today going to start on slide 4. All right. So what we're trying to do is figure out what's the domain and range of a reciprocal function. In this case, it's the one that we've been working on. All right. So if I click on this and just drag it, any pair of numbers, if I multiplied those two, I'm going to get 12. If I multiply those two, I'm going to get positive 12. But the coordinates, when you multiply them, is going to give you 12. If this number was a 6, then any numbers on here would multiply together to be 6. And it doesn't matter where. Those multiply to be positive 12. So I showed you a shortcut for like graphing them. Your first assignment in this is graphing these. And we did a couple yesterday, so let me just show you that real quick. So the other thing was, if you had this equation, okay, if I said, hey, sketch 6x, 6 over x. Well, what we know now, to sketch this is positive, so it's going to be in this quadrant and in this quadrant. And then I know the points that are on it are going to multiply together to be 6. So like I know 1 and 6 would be on there. Okay, so that gives me an idea. And then 6 and 1 is going to be on there. And then I know 2 times 3 is going to be on there. So that's enough points to get the general shape of it. So I can graph it pretty quick. And then just when these are negatives, -1, -6. Okay. You just make both of these negatives because now they're in third quadrant. So -2, -3. And then you can draw that one. And then -6, 1, -6, 1. So that's all you need in order to kind of have a pretty good idea of sketching these. Now, when you guys sketch them for your homework, all you need to do is just put one of these sets of numbers on it. Usually I pick the one that's in the middle. So I would draw this. Mine would look like that. And I would probably leave off these. Oops. Not that far. Mine would look like this, and that's enough information. Because just by looking at that, I know this is going to be 6 over x because of 2 and 3. So today we're going to take a look at, well, if you were graphing, what if you graphed y equals 8 over x? How would it compare to this graph? Or if you graphed 2 over x, how would it look different than this graph? Would it be less curve, more curve? Hey, that's what we're going to kind of play around with today. And then we're going to look at the domain, and then we're going to look at vertical and horizontal asymptotes defined using limits. Limits will be something that you have not seen before. Okay, there's two basic topics, well, there's three really. Three basic topics in calculus: limits, derivatives, and integration. So if you move on next year, whether you're doing it here or you're in college and you take a calculus class, that's all you'll do in your first year calculus is do limits. But I'll explain to you what they are kind of conceptually today. All right, so let's go over to this. Okay, so if we click on here and just look at the nature of the x-coordinates, that's going to give us an idea of what our domain is. Okay, so as I'm looking at this, I'm just looking at the x-coordinates there. And then kind of do the same thing over here and just look at the x-coordinates. So when we list the domain of something, all right, and there's no restrictions, a domain that doesn't have any restrictions in it means that you could trace this graph without lifting up your pencil. See, I can't trace this graph without lifting up my pencil to get to the other side. That tells me that there's going to be restrictions on the domain. There's numbers that aren't allowed to be part of this graph. All right? So, for example, can you think of an X number that is impossible to plug into this graph? Pardon me? 20? Well, remember this graph, it goes on forever. Goes on forever, goes on forever, goes on forever. It's 0. So if you were running this graph, or if you lived on this graph, your x-coordinate would never, ever be a 0. Because, like your address won't have a 0 as an x-coordinate. Because if I try to do that, I'm not going to hit enter, because when you divide by 0, somewhere randomly on the globe, a hole opens. And if there's a small child standing there by chance, they disappear. Yeah, because it's happened like with my keys and my first phone. Somebody divided by 0 and it disappeared. But when we divide by 0, it's impossible. You can't do it. There's an error. You tried to divide by 0. You can't divide by 0. I just hope maybe a goat fell in and not a child. Yeah. Well, if it's a living thing, but it could be a tree, a rock, a pebble. If anything that's by that hole is gone, believe me. You ever? I don't know what it is, but I really shouldn't have done that. That was pretty irresponsible. Okay, so we know that 0 can't be in this. So as I trace this, I'm right now, if I could keep going, I'd be at like negative infinity. So I'm just looking at the x-coordinate. And as I move to my right, the x-coordinate gets closer and closer to what value? 0. All right. So if I was typing that in, to type math in on these, you hit this little icon down here. And now it recognizes that you're typing in math. Okay, so I'm going to go parenthesis, and I'm going to type negative, and I'm going to spell out the word infinity. No, it should change. It'll change into the symbol if you spell it right. Let's try it again. Negative infinity. There you go. Yes. No. You can't, because, well, here's why it is. So that's going to go up to 0, but it's not going to include 0. So I'm going to put a parenthesis there. So what this is getting close to 0, but it never touches 0. It'll get infinitely close, and you'll see that here in a little bit with another animation that I'm going to show you. If I could keep dragging this point, if I keep dragging this point, the x-coordinate is going to get really, really small. Okay, now I can't go any further because, the graph's only so big. Now, you can't put zeros in. So we're going to say or. So I'll just go capital U. Okay, and then that's not the one I want. There we go. And then this branch of the graph, the x-coordinate is very close to 0, but doesn't include it. And now as I move to the right, the x-coordinate is going to move out to positive infinity. So this part would be from 0 to comma infinity and beyond. Okay, that would be my domain. Now, that's interval notation, which in this case is kind of cumbersome. You know, writing all this stuff, it's easier. You could also just write this. All real numbers except x. I don't think do we have a cannot equal? Is there a not equal on here? I don't think so. An equal sign with a slash? Don't think so. Factorials. The explanation for factorials. So I could say all real numbers except 0. I could write it like that. That's the same thing. That's just another, that's how you really think about it. Okay. And then there's another notation that I'll show you on your notes after we do the range. Okay, now let's do the y value. So the lowest y value on this graph, well, there isn't one. Now I'm looking at the y values. So right now I'm at negative 12 because I'm limited by the edge of the graph. But I could go as far down as I wanted to. And then as I come upward, I get the y value now is the one that's getting closer and closer and closer to 0 and not reaching it. Okay, so my range is going to be written the exact same way. Okay, it's pretty much just going to be this, Control C, and then I'm going to go math, and I'm going to go Control V, and change the word from domain to range. Okay, and this would be all real numbers except 0. Except y equals 0. And really this should be except x equals 0. Okay, so if this was a function machine, while you're writing that out, if this was a function machine, and you put stuff into a function machine and other stuff comes out, well, you could never put in an x. So if that was your machine, I'm sorry, you can't ever put in a 0. If you put a 0 in, you get fired because it'll break it. Then the range is basically saying a 0 will never come out of this machine. You can wait all day. Hey, I'm waiting for a 0. It ain't coming. A 0 will never be the output from a reciprocal function. All right, now if you go over to the packet that I gave you today, that you picked up, let's see. There's another way to write this notation. I just want to show it to you so that you understand what it is. Okay, this right here. This is another way of saying the exact same thing. So what this little symbol means, this funny looking E. Okay, so this funky symbol right there, that just means is a member of or is an element of. that curvy E. Yeah, and this fancy looking R is the set of real numbers. So just so that you understand this notation, this is the same thing as saying x is a real number. It's an element of the real numbers, and it can't equal 0. So this means the exact same thing as saying x can't equal 0, or, see, math, there's so much notation in math. You know, there's like 5 different ways you can say one thing, which can be kind of confusing. In set notation, that looks like this. It's like saying a word in different languages. They all mean the same thing. They just sound and look different. Okay? So this notation, or this notation are all the same thing. Okay? It all means the same. It's just different ways of writing it. One isn't right or wrong. That's just the way it is. Okay? All right. So I just wanted you to be aware so that when you see that, you understand what this means. Okay? All right. Okay, now what we're going to do is we're going to look at why when we take a line and we write its reciprocal, it turns into a curve. So how does that turn into, as this comes in, it shoots up like that? Or if it comes in this way, it shoots down. How can that be? Okay. All right. So the reason why a graph shoots up or shoots down like that, if you just think about this, if I took the number 1, okay, and I divided it by different values of x. Okay, so watch what happens here. I'll just take my calculator. As x gets smaller, what happens to this quotient here? Okay, so as I take smaller and smaller values of x, what happens to this, the answer to this division expression? Okay, it's going to get smaller. Okay, so what the heck? Get out of here. What is that? Cancel. Okay, so you're dividing a number by a really small number. Okay, so if I did like, we'll start with like 1/10. Okay, so 1 divided by 1/10. Okay, 1 divided by 1/10. Okay, oops. Let's do it like this. Let's be a little smarter. I'm going to go y equals, and I'm going to make this reciprocal. 1 over x. Get rid of that stuff. Okay, 1 divided by x. And I'm going to put that into a table so it's easy to do a whole bunch of calculations on it. So I'm going to go second table set. Yes, good. Second table. Get rid of this stuff. So, okay, clear. Clear. Okay, so I'm going to put 1/10 in. And I get 10. Okay, so when I put 1/10 in, the answer I get is 10. Okay, if I put 1/100th in, okay, I'm going to get 100. 1 divided by 1/100th is 100. Okay, so if I put 0.0 in, 0.01, I get 100. Okay, I'm going to pick a smaller number. What about 1,000th? Right. So I keep putting smaller numbers in, but when I put them into the reciprocal function, they start getting really big. Okay, that's 0.0001, this one right here. And you can see now the number's getting bigger and bigger. So as this number gets really, really close to 0, okay, as that number starts to get close to 0, what does this number start to get close to? So when I kept putting, when I put smaller numbers in, right. So as this side gets smaller, this value gets bigger. And if I was really, 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 really close to 0, and I put that in there, I'm going to get a really big number. Okay? So as the bottom, the reason why it curves is you start to put in smaller numbers, this graph starts, the y values start increasing really fast. All right, so overall, just write this down. All right, and now this is going to be some notation that's new to you. As x tends towards 0. Okay, so watch up here. Put your phones away. What sitcom are you watching? He's old flip. He doesn't even know. What are you watching? You got to tell us. Oh, that is a good show, but not right now. Okay. It is good, I have to admit, but probably not the right time. Okay, so when you see this, this means as x tends towards 0, or as x approaches 0, okay, the y value approaches infinity. The y value is the answer. So as this number got smaller, the answer got bigger. Okay, now what would happen if x went to infinity? Very good. So if this number got as it gets bigger and bigger, when you take 1 and you divide it by a really big number, your answer is going to get smaller. Okay, will it ever reach 0? No. It'll get close to it, but it won't reach it. Okay? This, you can't reach infinity because infinity is not a number. It's like an idea, like saying faith. Okay? It's not something you can reach. All right? So this concept of getting really close to something but never actually reaching it is known as a limit. As one variable approaches a certain number, the other variable approaches another number but doesn't reach it. Okay, so here's this kind of concept. If I had a box, Okay, what I'm showing you right now is a famous paradox called Zeno's paradox. Do you know what a paradox is? Okay, explain it to us. What is it? What is a paradox, Ryan? Exactly. Very good. I couldn't have said it better. All right. So here's an example of Zeno's paradox. So Zeno was this Greek mathematician, and he wanted to go for a walk one day. This is a true story. I mean, he's the one that came up with he's got like 40 really famous paradoxes. And his one paradox was built around this story. He wanted to go to the park. Okay, now let's say that the park they didn't use miles back then, but I'm just going to say the park is 1 mile away. Okay, and here's Zeno. And Zeno is walking at a speed of 1 mile per hour. Okay, and here's the park. Okay, how long is it going to take him to get to the park? Should take him 1 hour. Okay, but yes. What? Oh, man. What the heck? They're missing Zeno's paradox. Boy, I'm glad you told me. You can't miss Zeno's paradox. You guys are like, yeah, you can. Thanks for telling me. Where did everyone take off? They're like, Krolak. Are they all gone? They're all gone. I don't blame them. Oh, well. Yeah. Okay, so back to Zeno. Now, here's what Zeno is saying. If I walk to the park and it's 1 mile away, okay, if I take the time that it takes me to get halfway to the park, so the time to reach halfway is going to be 1/2 whatever this time was, a half of an hour, right? Okay. Then if from this point, I cut that in half, then how much time expired right here? Yeah, or a quarter. So half an hour, a quarter of an hour. Then if I walk to here, how much time? I'm sorry? 1/8. And then half that distance. What? Right. He'll never get to the park, but remember, this is time. So half of an hour, a quarter of an hour, 1/8 of an hour, a 16th of an hour, a 32nd of an hour, a 64th of an hour, a 128th of an hour. What's this time going to add up to? I keep adding to it. Infinity. Because I keep adding. So this has got to be growing. Well, so Zeno was like, well, I'd never reach the park because it would take me an infinite amount of time. Well, we all know that that's nonsense. But following this reasoning, it should take me, instead of an hour, infinity hours. Okay? And we all know that's not true. So the way that you prove that it's not true is think of this box as having an area of 1. Okay, if I take this box and I take half of it and I shade it in, then that's half. And then I take half of the remaining and shade it in, that's a quarter. And then I take half of the next one and I shade it in, that's an eighth. You see I'm creating the same sequence as Zeno did? But his, he thought, added to infinity. Okay? Right. Because as I keep cutting this box into halves, I know I'm never going to create more area than there is in the box or in the square. So that tells me that this, I can keep cutting it in halves. I could keep going and going and going, but the answer would get closer and closer to 1 instead of infinity. So now it makes sense in real life. Yeah, it's going to take me 1 hour to get there. Okay, so this is always used to as an example of how limits work. You'll never reach 1 in this box because you could always cut whatever's left into another half. All right, it'll always be there. You could cut no matter how small it is, but you're going to be really, 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 really close to 1. Okay, so that's this idea of a limit. Okay, now limits, when you have a limit on 2 sides of a number, that tells you that you have what's known as a vertical asymptote. Okay, that means it's a number that the graph will get close to but never ever reach. All right, so if we go back to our what happened to my page? Our investigation here. Okay, go on to the next one. All right, so what we want to do is describe the behavior of a graph. Now, when I say the word behavior, we're not deciding, is this a good graph or a bad graph, or, arrogant, or it has nothing to do with emotions. Behavior has to do with the y coordinate. What's the y coordinate doing as we start moving in different directions on this graph? Okay, so the behavior is described using a value, a number, but you know that it gets close to it, but it never touches it. Okay, and that idea, that concept is known as a limit. Okay, so if you click on that little hyperlink, I put a link to a GeoGebra inside of a Desmos. These companies are arch rivals. I'm trying to bridge the gap here. So if you click on that, and we'll make it bigger. This little applet here, this little animation, is a way of showing limits. Okay, and limits, when you have a limit, you're going to have a vertical asymptote, if it ever loads. So click on your link, because maybe yours will work faster than mine. And once you get yours open, we're going to change this to the function that we were working on. So you can just click on it. And ours was 12 divided by x. So we'll put that guy in. Okay, you can zoom out, see what it looks like. All right. So what we're going to look at is what happens when we take that blue dot and we move it towards 0. So down here at where it says test value, just put in a 0. Well, actually, Yeah, you can just put in a 0. Now look what happens look what it said the y coordinate is. Infinity. So as I take this dot and I start moving it towards 0, look at the y coordinates. The y coordinates are these numbers here on the right of the equal sign. As I get closer and closer and closer and closer and closer and closer, okay, those y coordinates start to get really, 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 really big. Okay, so for example, if I got super close to 0, 0.00001, that's really close to 0. The y value would be 1,200,000. Way up here, you can't see it. Okay, so as I get close to 0, my y value shoots to infinity. Okay, now look up here where it says LIM. This is something you haven't seen before. All right, if we look at the bottom one, I'm going to explain to you what this notation means. When I was dragging the blue dot towards 0, what side of 0 was I on? The positive or the right. Okay, so when you see this 0 in this context with a little plus sign, what that means is you're moving towards 0 from the right of 0. That's what this 0 plus means. So what this means is, as I get closer and closer and closer to 0, the y coordinate gets closer and closer to infinity. This is called a one-sided limit. Now, what do you think this one means? The one right above it. What do you mean negative? No. It has to do with what side of 0 you're on. So watch, see how I'm dragging the dot now? I'm coming in from which direction? The left, or negative. So as I move towards 0 from the left side, see the middle limit here? As x approaches 0 from the left, the y coordinate approaches negative infinity. So if I got really close to 0 on the left, like negative 0.000001, look what happens to the y value. It's really negative, big time, negative 1,200,000. So the minuses and the pluses tell you which way you're moving from. This is approaching 0 from the right. That's the bottom limit. This is approaching 0 from the left. That's the middle limit. The one on the top is called the double side limit. See how it's got a question mark? Because one side you're going to infinity, the other side you're going to negative infinity. They're going in different directions. So the double-sided limit doesn't exist. They're not both approaching the same thing. They're going in opposite directions. So this limit, D and E, does not exist because they're not approaching the same number. Okay, that's what this means here. So when you go back to your investigation here, what if I was going to read this, it would say the limit as x approaches 0 from the right of 12 over x equals what? Okay, so let's look. 0 from the right. So yes, very good. It's going to be positive infinity because I'm coming in from the right. Okay, so this would be positive infinity. Okay, go to the next slide. What's the limit going to be? Say, Rachel, what side of 0 am I on? The left side. That's what that little negative means there. So now I'm to the left of 0 and I'm coming in hot. I'm getting closer to, I'm coming in closer, 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 closer. And then I see, y equals 0. No way. And I head this way. I'll never cross that line. It's like an invisible barrier. So if you have a graph and it's doing what this graph's doing, you know that there's an asymptote that's causing it to happen. It's kind of like yesterday when we talked about a black hole. If light is being bent and I don't see a planet next to it, then there's a black hole there because something's making that light bend. Yes?
Is there any hyperbolas that aren't asymptotes?
No, all hyperbolas will have an asymptote or more than one. So you can have hyperbolas that have 2 asymptotes. No, this is one vertical asymptote. And the reason why it's only one, what's the only value you can't put into that? 0. If I could put more numbers in, let's say that my hyperbola looked like this, then where's its asymptotes? Yeah, there'd be an asymptote at 1, and there'd be an asymptote at 5. So my graph's going to end up doing something, and we'll talk about these later, like that. Oh, yeah, that should be, let's see. Yeah, that should be plus. You can't put a -5 in there. Things break. You can't put a 1 in there. So anything that's not allowed is what creates asymptotes. What you guys just learned was the definition of an asymptote using limits. All right, let's go back to the next guy here. And then we're just about out of time. Okay, the last two that I want you, so this one was going to be, what did we say, negative infinity. All right, let's see if we can do these next two and then we'll call it a day. Okay, that's the definition of a vertical asymptote. Because these go to infinity, something's going on there. There's an imaginary line that's like an electric fence. Okay, and it's a vertical line, so it's an equation like, in this case, x equals 0. All right, now, how about this limit? So now, as x goes to infinity, so right now, I'm on my way to infinity. What's the y value on its way to? Okay, now look at this. There's a 0 with a plus and a 0 with a minus. Right, in this case, you're coming into 0 from above. So now this means I'm approaching 0 from above. And now if we were going out to negative infinity, we're now approaching 0 from below. So this would be 0 from below. All right, guys, we'll pick up with this mañana.